Let's go ahead in our topic X-ray diffraction. Today we are going to discuss on X-ray diffraction techniques. There are two principal X-ray techniques. First is powder method, in which the materials being studied are in polycrystalline form, and second is single crystal diffraction method, in which the sample is a single crystal of dimensions of several tens of micrometers or larger. Today we will discuss only on powder method. Powder X-ray diffraction is used mainly for phase identification and the determination of lattice parameters and lattice type. In this method, the materials being studied are in powder form. A powder sample contains an enormous number of very large crystallites, typically 0.1 to 10 micrometer in dimension and oriented at random. An X-ray beam striking a polycrystalline sample is scattered in all directions. At same angles, constructive interference occurs. As a result, each set of planes of atoms with lattice spacing d gives rise to cone of diffraction intensities. Each cone consists of a set of closely spaced diffracted rays, each one of which represents diffraction from a single crystallite within the powder sample. With a very large number of crystallite, these rays merge together to form the diffraction cone. This is the setup of powder diffractometer, which uses an electronic detector to measure the angle of diffracted beams. This schematic diagram of powder diffractometer operating in reflection mode, in which the X-ray scattering occurs from a sample mounted as a flat plate. For a weakly absorbing compounds, the sample may mounted in a capillary and the diffraction data collected in transmission mode. So in this method there are two modes for diffraction data collection. First is reflection mode and second is transmission mode. Now the scanning with this detector around the sample along the circumference of a circle cuts through the diffraction cone at the various diffraction maxima, and the intensities of the X-rays detected is recorded as a function of the detector angle. You can see in this graph, this is the form of typical powder diffraction pattern, showing a series of reflection as a function of angle. The number and position of reflection depend on the cell parameters, crystal system, lattice type, and wavelength used to collect the data. The peak intensities depend on the type of atoms present and their positions. Nearly all crystalline solids have a unique powder X-ray diffraction pattern in terms of the angles of reflection and their intensities. In mixture of compounds, each crystalline phase present contributes to the powder diffraction pattern. Its own unique set of reflection angles and the intensities. Typically, the method is sensitive enough to detect a small level for 5 to 10% by mass of a particular crystalline component in a mixture. The powder method used in the identification of unknown materials and in determination of sample purity, determination and refinement of lattice parameters. It is also applicable for investigation of phase diagrams and in investigation of new materials, determination of crystallite size, structure refinement, ab initio structure determination, and in phase changes and expansion coefficients. Now these are the typical use and information extracted from this method. Now the powder X-ray diffraction is mostly used to characterize and identify phases and to refine already known structure rather than to solve unknown structure. In material science and in chemistry, it is often required to synthesize new materials. Although large single crystals are typically not immediately obtainable, microcrystallites sufficient for powder diffraction may be readily available. Powder diffraction is therefore one of the most powerful method to identify and characterize new materials in these fields. Basic crystallographic information such as lattice parameters can normally be extracted easily from powder X-ray diffraction data, usually with high precision. The presence or absence of certain reflections in the diffraction pattern permits the determination of the lattice type. In recent years, the technique of fitting the intensities of the peak in the diffraction patterns has become a popular method of extracting structural information such as atomic position. The analysis involves fitting a calculated diffraction pattern to the experimental trace. This is known as Rietveld method. This technique is not as powerful as the single crystal methods, for it gives less accurate atomic positions but has the advantage of not requiring the growth of a single crystal. So in the next lecture we will discuss on second X-ray diffraction method.